Hi there, and welcome to another episode of Mr. Carlson's Lab. So, in the past, there's been quite a bit of interest in this big old Gates AM broadcast transmitter here, so I figure it's about time to do a video on it. So what I'm going to do is show you how all the meters work and what they represent. We'll take a look at the knobs on the face here, and I'll show you how they control the transmitter, and then we'll go around the back side, and I'll take you inside the transmitter. Yes, it is big enough that I can stand inside it and comfortably show you around. Now you'd figure, from the physical size of this thing that it must be a huge power transmitter, but actually it only makes 250 watts. The model number for this transmitter is a Gates BC250GY, and you can see the 250 is the 250 watts. Being only 250 watts RF output, it's perfectly legal for ham radio operators to own these things and convert them into the amateur radio bands. And that's exactly what I've done with this one here. It's in a completely different band now and everything. So way back in the day when this thing was in service, in broadcast service, it was in service from about the year 1948 to the year 2003, and it played country western music. That's what this thing did. This was classified as a nighttime transmitter, and they also had a daytime transmitter. These were located in a remote shack. This wasn't in the actual radio station or anything like that, and the signals were fed out to this shack and through these transmitters, and then it would broadcast. Now, what would happen is, the engineer would come around every now and then and, make sure all the settings were right, and they would just leave. And you could leave these things unattended because they were so incredibly dependable. Nothing really went wrong with these things. In fact, these Gates transmitters were incredibly dependable. It's still around, Now, the reason that they had a nighttime transmitter and a daytime transmitter is basically due to regulation. At nighttime, the broadcast band really likes to travel, I guess you could say. You can look at it like this. If you got a rock and you try and skip it on water, you can get a rock to skip on a pond or something like that. Well, the radio signals do the same thing. They go to the upper atmosphere and they skip along the upper atmosphere and come down in different portions of North America. And sometimes that'll interfere with other radio stations in other parts of the world. So what they did to try and stop that is they had an antenna system that they could electrically change the direction in which the signal is radiated. So they would fire the signal in a different direction and they would drop the power down. And that's what they did with this. They would drop the power down and fire the signal in a different direction. And then in the daytime, because there are no conditions, they would go to the high power transmitter and then change their direction again. So this is really common in a lot of these radio stations. They would actually, turn the power up and down. Now, most of the later transmitters, they would have a dual power setting, a nighttime and a daytime setting. And it was actually just a switch that the engineer would click and it would go, say down to 250 or 500 watts, and then it would go up to full power or whatever. Now, I have some daytime transmitters as well. Actually, they're dual function transmitters. They're very large ones, and I'll show you those here in the near future. Really nice looking transmitters, beautiful RCA logos on the front of them and everything like that. These transmitters are weighing down another portion of the property right now. They're not restored, so they're basically sitting out there, and they weigh as much as probably a full-size Chevy truck. They are just huge, huge transmitters. The modulation transformers in these things, or the audio transformers, are monstrous, and they require a few people to move the transformers. You can't move the transmitters without moving the transformers out of them because they're just so incredibly heavy. So that'll make another interesting video in the future here. Really nice looking transmitters, possible future projects. We'll see how this goes. So what I'm going to do is reposition the camera here, and I'm going to put the RF output into a dummy load. So what a dummy load is basically a non-inductive resistor in a big can filled with oil. Now this is a 1,000 watt dummy load, but since this is 250 watts AM, it's continuous power, that 1,000 watt dummy load gets hot very fast. And unless I want to make French fries with that oil, I'm going to have to keep the explanation quick when I turn this thing on here. So that's what I'll do now. I'll get that all set up, and then I'll show you exactly how everything works here. The very first thing to do in the startup procedure of a transmitter like this would be to turn on the filament control. So if this was in a radio station and the thing was completely off, the very first thing that the broadcast engineer would have to do would be to light the tubes up inside. So for those of you that aren't familiar with vacuum tubes are much like incandescent light bulbs. They have a filament structure inside that needs to be warm in order for the vacuum tube to work. So in order to turn on the filament supply, you have to push this little switch right here. Now by pushing that switch right there, you'll see that both of these lights kind of glow a little bit dim. What's happening inside is there's a thermal delay tube in there that's preventing the engineer from accidentally turning this thing on before all the vacuum tubes are warm. There's a mixture of two different types of vacuum tubes in here, and one of them has to wait a while to warm up. You'll see when it's warm, this light here will come on. There it is right there. Now it's ready to put into service. So there's two types of vacuum tubes inside of this. One is called directly heated and the other is called indirectly heated. The indirectly heated vacuum tubes have a filament inside of a pipe inside of the vacuum tube itself, and that filament has to heat that pipe up orange, and when it's orange, it'll emit electrons. Now, that takes usually between about 10 and 20 seconds to warm up. The directly heated vacuum tubes, which are the big power tubes and the modulator tubes, modulator is basically a big audio amplifier inside this thing, they are pretty much ready to go instantly. So you turn it on and they'd be ready to go right now because they light up. The actual filament structure itself is the cathode. It doesn't have to heat up a pipe or anything. So since there is a mixture of both kinds, there's a thermal delay in here that just makes the engineer wait before he turns it on. If you turn it on before that time, the audio would slowly come in and it would sound crunchy and distorted. And, it's just, you have to wait for everything to warm up properly. That's what it's doing. So this thing is already into a dummy load and it's ready to put into transmit mode. So I'll just give you a quick overview of what it looks like when it's in transmit mode. Everything is pre-tuned and I can just do that. But what I'll do here in a moment is I'll move the camera and I'll get a little closer to the meters here. And I'll show you exactly what needs to be done in order to make this thing go into transmit if you were to turn this on for the very first time. Okay, so I'll just turn on the plate switch right here. And you can see all the meters are moving here and everything's happening. So the plate switch on a transmitter like this puts this thing into transmit. So technically right now the thing would be on the air. Now the plate switch inside this thing turns on high voltage inside this thing. These transmitters run on very high voltage. They're not like a solid state amplifier. Vacuum tubes are a relatively high impedance device, and in order to make them work correctly, they require high voltage on the plate or on the anode so that they can do their job. So if you were to look at a vacuum tube like a transistor, a vacuum tube's plate would be much like the collector on an NPN transistor, or if you're looking at an N-channel FET, it'd be much like the drain on an N-channel FET. So that's basically what the plate is representing here. Now I'll get a little closer and I'll show you all the voltages and I'll explain what all the meter readings do here in just a moment. So there's high voltage all over inside this thing, and on the back side of this unit there's a big door that opens up, and there's a thing called a safety interlock switch, or sometimes known as a dead man switch. So when you open the door, it automatically cuts the high voltage so that the engineer, if he forgets to turn the plate switch off, he doesn't get promptly ejected out of the back of the unit, land halfway across the shop, and need resuscitation. If you come across the high voltage in something like this just once, you're dead. That's it. It's really that strong. The transformer that takes the 220 service that comes into this and steps it up to about 1500 volts, it gets rectified and it's 1500 volts DC. There's a lot of current behind that 1500 volts and it only takes once, so you can't take any chances. So there's safety interlocks on this thing that are definitely needed. Now, defeating the safety interlock is definitely not recommended. But, in some cases, the engineers have done it in the past, and you have to be super, super careful because, when that red light's glowing, that means trouble if you're in the backside of this thing. So what I'm going to do is just get the camera a little closer to the meters here, and I'll explain what all the knobs do. The first meter that we're going to look at is this meter right over here. This is the only one that's active. And then I'll come over to this side, we'll look at this one, go up to the top, and work our way across that way. So the first thing that the broadcast engineer is going to adjust when he turns on this transmitter, so what he's doing is he's applying the filament voltage here. He doesn't even have to wait for the green light to come on. If this is the very first time, he's going to be very quickly looking at this meter that's active over here, making sure that it is around 10 volts so he can at least relax. If it's around 10 volts, then he's going to try a fine adjustment and get it to 10 volts. So I'll explain a little bit more about that here in just a moment. So first of all, it's very crucial that the filament voltage on 5 of the vacuum tubes inside this transmitter sits right at 10 volts. So the reason being is these Gates transmitters are designed to be in service 24 hours a day, 7 days a week. That's how they're intended to be operated. Whether, a station chooses this thing to be a nighttime transmitter or whatever is up to them. But if this thing is on 24 hours a day, 7 days a week, any little over voltage on the filaments puts a dramatic life reduction on 5 of the vacuum tubes inside this. You got to remember, just a little bit of over voltage, say over 8 months, is a dramatic life reduction. So the broadcast engineer is going to be tuning this for exactly 10 volts. So he's going to be turning a potentiometer over here that Gates has provided. Right here, he's going to be turning this potentiometer to bring that down to 10 volts. Now, this is just a fine-tuning adjustment. Inside, there's a filament transformer on the bottom with a bunch of taps on the primary of that transformer. So just say the line voltage is higher than 240. Say it's up at 255 or something kind of extreme like that. What he's going to do is shut everything down and disconnect the service and go in there and move some taps around on the transformers. And then he's going to try things out. So what he's going to want to do is center the filament voltage control right in the middle. So he'd move this around and find the center. He would move those taps around until he can get the filament voltage right as close to 10 volts as possible. And then he's going to use that VR that I just showed you to fine tune this. And what I'll do is I'll just move the filament voltage control around and you'll see this rise a little bit. And then you'll see it fall a little bit. So right here is at about 10 volts right there. The reason I'm looking at this on an angle with the camera is just because there's so much glare and stuff here. So by having the camera on an angle, I can kind of avoid that. So it's pretty shiny. Now, this here potentiometer and the one right above it, that one here and this one here, are both just big variable resistors. So if you were to look behind here, and you'll see them here in a little bit, it's just a big porcelain donut with a bunch of nichrome wire wrapped around it. And then there's a carbon brush that runs along the track. When you turn the knob here, this carbon brush just moves along the track. So again, just like a big variable resistor is all it is, and it's in line with the primary of the transformer. So there's 240 coming up to this control here and then running back down to the filament transformer. It's the same thing for the power amplifier voltage control up here. There's 240 running up to this here as well. And all it's doing is just allowing you to vary the primary voltage on, that big plate transformer. So I'll explain this function here in just a little bit and why they've added that in. So the next meter we're going to look at is this one right here. This is the RF line current meter, and it's pretty much exactly what it says it is. This is an RF amperes meter, and this is just indicating the current on the RF line. So these meters are very often toast in these transmitters when you get them, and even when they're in service, these things, they end up going away and they just leave them dead, and they don't really take notice of it. You can use the other meters and kind of get away with it. The RF line current meter is, I don't know, it's an extra add-on. It's nice to have if it's working, but if not, you can get away with not having to use this thing. So what happens is most of these old Gates transmitters, and many of these old transmitters, are in a hut in the middle of a field somewhere out in the middle of nowhere, and there's an antenna tower beside the hut that's sticking up like a sore thumb. There's nothing around, and the thing's a lightning magnet. So, this thing has been in service from, 1948 to about 2003. So there's a pretty good chance that, some lightning has struck close to this big tower, 100-foot tower, whatever it is, sticking up beside this hut. And what that does is that destroys this meter. And this meter was fried, and it was fried but good when I got this thing. So this is a replacement meter. The two other broadcast transmitters I have both have fried RF line current meters as well. So again, most likely due to a very close lightning strike. Up here is the plate voltage meter. This indicates the high voltage that's throughout this entire transmitter. So those 5 tubes that I'm telling you about have a plate voltage of just below 1500 volts in this application right now. Now the plate transformer in this has been replaced, and it has solid state rectifier, so it is just a little bit higher, but in amateur service I'm not really too worried about that. I can work around that extra voltage. I think the solid state rectifiers were put in, probably in the 60s or something like that. I think it was written in the logbook when they changed over the 8008s. Those are mercury rectifiers, and they changed them over to these solid state rectifiers. So the 8008s, I believe they're mercury. They may be a xenon rectifier. I think they're mercury, though. I'd have to look that up again. At any rate, they're solid state. I'll show you what one of them look like. They're huge. They're really big, and they're full of diodes, really big diodes, too. So this here is the power amplifier plate current meter right over here, and this indicates the anode current, or the plate current, on the RF final tubes. So this is the monitoring the RF amplifier inside this thing. So in order to tune the RF amplifier inside this thing, you would basically monitor this. You would tune this control over here for a dip. All right, so you'd be looking for a dip in the plate current. And on the other side, you have a loading control, and you'd be adjusting that to get your desired loading. So basically, you're adjusting this thing to move the needle up a little bit, and then you'll move over to here, and then you'll be dipping it, bringing it into a dip again, and then back and forth and back and forth. This is quite an explanation to go through that in this video, and I'm not going to do that just because it really is quite in depth. If you guys are interested in learning how to load broadcast transmitters and just, amateur radio gear, vacuum tube amateur radio gear, you can let me know that down below in the comments. I have tons of transmitters here that I'm going to be going through in the future, lots of AM stuff and early sideband equipment, and even some very large RF amplifiers as well are waiting for the bench. So there's a lot of really neat stuff coming in the future. You can let me know if you're interested in learning this kind of stuff, and if you are, I'll be glad to put that in for you guys. So this here is the plate current, again, for the anode, and this is the grid current. So basically, this is where the signal goes into that RF amplifier tube. So the RF amplifier tube just before the tank circuit. So this is indicating the grid current, the current on where the input signal goes in, and this is monitoring the current on where that signal comes out. So these are both for the power amplifier, as you can see, PA and PA here. So if we move over here, we have the modulator plate current right here. Now this indicates the anode current for the two 810s in the modulator section. What a modulator is virtually a very large audio amplifier. And there's some very big tubes, and they're modulating a very large audio transformer. And a bunch of reactors. There's a bunch of very large reactors in here. I think one of them is 60 to 80 henries, for any of you guys that know about modulation reactors. So it's somewhat of a modified Heising setup. Really neat modulation system or scheme in this transmitter. So this will indicate two things. This will indicate the idle current for both of the 810s. So there's two 810s in here, and each 810 requires 30 milliamps of idle current. And in order to adjust it, you have to be in the back side of the transmitter. So when I put this into transmit, since there's two 810s, it should indicate 60 milliamps of just idle current. So what I'll do is I'll turn the plate switch on here, and you can see it's just above 50, and that's exactly where it needs to be. The modulation section, I'll just shut this off. The modulation section inside this transmitter is in class B. So it's imperative that the idle current is correct. Of course, they've figured out a situation for the lowest amount of distortion and, enough idle current so that, the tubes are going to be quite comfortable. So when music program or voice is being played through it, this thing here is continually bouncing around. This meter moves up and down because it's indicating the plate current on those modulator tubes. Again, modulator is just a fancy name in the transmitting industry, I guess you could say, for audio amplifier. So if we go over here, this is the RF driver plate current. So the tube that drives up those two RF final tubes is an 813, and this is indicating the anode current on that. And this is the filament voltage again. So if we look down here, we have a neutralizing control, and the neutralizing control is there to basically stop this thing from oscillating in two places at once. Now, this is not to be confused with parasitic oscillations. This is basically the transmitter trying to self-oscillate very close to the frequency that it's already set on. So say this thing was set on 690 AM or something like that when it was back in broadcast service. There's a chance that this thing may be oscillating at 697 or something like that. And this control here is designed to stop that from happening. You want to neutralize the RF driver and output section inside this transmitter. So basically, you're trying to get rid of a thing called transfer capacitance. And that, again, is another big explanation. Neutralizing is very important in amateur radio gear as well. So in the old AM transmitters and a lot of the sideband equipment. So there's a bunch of different ways that you can do neutralizing, and there's a very easy way that's very effective, and I'll show that to you guys in the future here if you're interested in seeing that. Again, you can leave that below in the comments if you'd like. Right below this is the driver tuning. So this tunes the plate and the actual driver tube to the grid of the RF output tubes. So when you're tuning this control here, you're looking for a dip on this meter here, and you're looking for a peak on the power amplifier grid current meter. So you're looking for a peak here, and you're looking for a dip here. Again, quite an in-depth explanation. Maybe one day what I'll do is I'll completely detune this thing, if you guys are interested in that, and I'll start from point A, and I'll just tune this thing up from being completely detuned, if you're interested in seeing that. Down here we have two little indicator lamps that just indicates the heaters on the crystals. The crystals inside this transmitter are heated. So basically a crystal with a filament around it and a bimetal strip that just clicks on and off and on and off and on and off to keep it at a regulated temperature. By doing that, you get a very, very stable crystal standard in here, and the tolerances for these transmitters is extremely tight. You know, they got to be, if it's at 690 AM, it's got to be at 690 AM and nowhere else. And so this is the reason that they have these crystal heaters here. So there will be one that's in service, and they can have one acting as a spare if one goes down or something like that. Now, it's very important for the output as well to be right at 250 watts if it's supposed to be. Now, the plate voltage here, you can see on this is, for my service is going to be up around, 1500 volts up here. But when this thing was actually in broadcast, looking down here at the power amplifier voltage, if for some reason it was a little over 250 after they've adjusted the loading and the power amplifier tuning, they could trim it with this. And that's what this VR or this variable resistor here is for, the power amplifier voltage. Again, you're just kind of trimming the primary voltage on that very large plate transformer. So just to, get it right at 250. So again, the regulations are very sticky. If it's supposed to be at 250, it has to be at 250.00. Just before we do go inside, you may want to see what all the meters look like when this thing is actually on. So what I'll do is I'll turn on the plate voltage here, and I'll give you a view of all the meters here. So that's the RF line current right there. And that's the plate voltage. You can see it's just below 1500. The power amplifier plate current is about 350 plus milliamps. Power amplifier grid current is right at 100 milliamps. The modulator plate current is just at its idle current, which is 60 milliamps there. There's no modulation happening, so it's just going to be stable. The RF driver plate current is just a little bit below 150. And then again, we have our filament voltage, which is at 10 volts. And that's what all the meters look like when this thing is just sitting here idling. Of course, again, when there's modulation, this meter here is going to be bouncing around, and the meters will all be moving just a little bit. The plate current meter will jiggle a little bit, and of course, plate voltage will move a little bit as well, because everything starts to draw current at that point. At this point, I'm just about ready to head on inside this transmitter. So people like to say this thing is about, the size of a refrigerator. I would say this is about the size of 5 refrigerators. It's a pretty big unit. You'll notice that the miking sounds a little bit different right now, and that's because I have to use the mic on the camera. I can't fit an external mic behind this unit. It's pretty tight behind there. So you can see the green light is on. That means the filaments are on. And if we look inside, see the 810s in the RF section are on, and the 810s in the modulator section are on. And in a moment, we'll be up close and personal to those tubes. Before I go inside this thing, I want to make sure that the safety interlock is working on the rear door. So if I press this, nothing should happen. The light will glow, but nothing happens. That's exactly what's happening. We look up here at the plate voltage, nothing's happening. Normally, if I press this, I would hear a big clack noise from the plate actuator relay. And the relay would, of course, energize the primaries of that transformer, and it's pretty audible when that plate transformer is on. The whole cabinet hums because it's sitting on the floor of this transmitter. So none of that is happening, and that's good. Normally, again, it would stay on, and then in order to cancel it, I would have to press this button. So let's head on around the back side of this transmitter here. We've got the widest angle lens on this thing that I can find, so right now I'm just kind of peeking around the corner, and in a moment we'll just head on inside so I can kind of get a wider view of things like this. So this whole chassis that you see right here is the modulation chassis. So that large black transformer that you see on the bottom right here is the power transformer for the chassis. There's a rectifier tube there and that thermal delay that I talked about earlier. That white cylindrical transformer that you see is where the audio signal comes in from the radio station. These two 6L6s take that signal and then drive this interstage transformer. That interstage transformer drives the grids of these two 810 modulator tubes. The signal is present on the plate and goes down to the floor, and then there's a modulation transformer on the floor, and I'll point that out here in just a moment when I can get a little bit closer to that. You can see that there's some very large resistors on the wall, and you can see those two big variable resistors right here for the filament and the plate transformer, the fine adjustments. And I'm very close to the 813 driver tube right now, and right close to these 810s here, and the plate choke. So I'll just step on inside the cabinet. You can see I haven't dedusted anything or anything. I just pretty much removed the rear door, and now I'm standing inside this unit, and it's pretty warm in here. So you can see I'm completely inside. So this is a Varactor tuned VFO that I designed quite some time back, and this is what is controlling the frequency on the amateur radio bands. So this here is a 10-turn 10K potentiometer. It goes into this box, and it basically just moves around a Varactor diode. So the VFO that's inside here is at 135 degrees Fahrenheit, 24 hours a day, 7 days a week, and yeah, it's nice and warm. So it's controlled by an NTC type or 10K ohm thermistor, and that's pretty much controlling a big resistor on the VFO itself, and it just keeps it right at 135. So there's a bunch of aluminum foil lined in here on some thick foam, and the whole thing is basically insulated. It's kind of like a small thermos, and yeah, it just insulates it, and it gets to 135 rather quickly, and it just stays there. So it works very well. One day when I go inside there and do some adjustments, I'll come on in here with the camera and I'll show you exactly what's behind this. So yeah, basically open this up. There's a small hole in some of the styrofoam to poke some of these tuning tools in to make some adjustments here. You can see I even designed the little adjustment tools to fit in there because everything is so tight. So temperature and 15 volt supply potentiometer adjustment tool, and the oscillator and buffer tuning tool. And this here goes into another thing that I've designed in here, which is this chassis. I'll have to stand up here to show you this chassis. This entire chassis right here is the driver for the actual driver. So the VFO signal comes out here into this driver chassis. I guess you could call it a pre-driver. And it heads on into this tube right here, which is a 6Y6. This drives up this 5933. You can see it's all really dusty. Haven't dedusted anything in here. This stays on 24 hours a day, 7 days a week as well, because the power supply for this is all inside that chassis. And these tubes have been glowing for years, and they still work just fine, as you saw, putting a signal into that dummy load. So at any rate, so it goes into there. Anyways, the signal gets amplified by this tube. So this is more of a buffer. Gets amplified by this, and then it gets put out into this coil, goes up this lead into the driver tube here, which is an 813. The signal gets amplified and then gets put through here into this coil here. This is what tunes the coil, that big potato slicer you see right there. And then the signal goes up this line right here into the grids of these two 810s. And these are the RF output tubes. And to give you an idea of the size of these 810s, you can see the size of my fist to the tube. These are parasitic traps to stop these things from oscillating in places that they're not supposed to be oscillating, and it definitely needs these. So that's what these are here for, This here is the plate choke. To give you an idea of how big that is, this is a standard choke that you'd find in a normal old radio. You can pretty much just stick it between there. Pretty large stuff. This here is basically kind of like a blocking capacitor in a vacuum tube amplifier. It just keeps the DC off of everything. So the signal comes out here, the RF signal's on here, heads to the capacitor, down through here into this larger potato slicer. So there's a small one there and a larger one here. So this variable capacitor tunes this inductor here. This is the power amplifier tuning capacitor. You get an idea of the size of the inductor here. And then the signal travels along this line here, goes into the loading capacitor. So there's not enough capacitance in this capacitor here, so there's a fixed amount that's bolted to the wall here. So this big old capacitor, this is a mica capacitor and can deal with quite a bit of current. These are rated at 13 amps at about 1 megahertz, so quite a large capacitor. And at any rate, the signal comes out here and then goes through that RF amp meter, and you can see right to the antenna. So now you can see why that these meters go bad if there's a close lightning strike. The antenna is just right into that meter, very first thing, right? So that's what that's for. So if we take a closer look at what's on the floor here, that's the door clanking behind me. These are the rectifier tubes, or the actual solid state replacements for the rectifier tubes, which were 8008s. You can see the size of these things, how big they are. Big diodes is what they are. So this basically takes the AC, turns it into about 1500 volts DC, and that's present there, and then runs out and gets filtered by a bunch of large reactors here, filter chokes. This is the plate transformer right here, and filament transformers here. These are the filter capacitors for the high voltage supply. It only takes about 10 microfarad or so in order to filter this all out. So that's the way it works. Lots of filter chokes and stuff in here, so you don't need a whole lot of capacitance. This is the mod transformer, to give you an idea of the size of the mod transformer. So this would be equivalent to a big audio transformer if you're an audio amplifier guy. So you can picture how big that audio transformer would be. Pretty large stuff. And this is the modulation reactor back here. So that's that 60 to 80 Henry choke I was telling you about. Somewhat of a modified Heising setup. Very neat setup. There's lots of big chokes and transformers down here, filament transformers. This is the plate relay right here. This is what turns on this large plate transformer and gives us our 1500 volts. That's that. This is a bunch of safety relays here. So if this thing is in a remote hut somewhere out in the field and something goes wrong, say one of the 810s becomes unruly and starts arcing and sparking or doing something like that, or there's some overcurrent situation, what will end up happening is one of these relays will actuate and then just cancel out the plate relay. So that's what these things do here. You can see there's 3 monitors here. If we look here, we can see some very large resistors. You see how big those things are. And up close and personal here with these 810s on the modulator chassis. These VRs right here are what adjust the bias. So each 810 requires about 30 milliamps of idle current. So this adjusts the bias right here. So this one's for this tube, and this one over here is for this tube. Kind of neat looking Art Deco, Bakelite knobs here. You can get an idea of how big that interstage transformer is. About the size of a, I don't know, standard 50 to 100 watt audio transformer, I'd say. Driven by those two 6L6s right there. Kind of drive hungry tubes, big triodes. In order to service this, is very simple. You just remove this screw right here and this whole thing just hinges open and you can get right underneath the chassis. You can see it's on hinges right here. So lots of wires joining everything. So the thing actually disassembles not all that hard. All you have to do is just remove all these screws here. There's one here and then there's another one here and all the way down the side. And these panels just kind of lift and pull off the wall, so you have to disconnect all the wires and everything. So, it's a little bit easier to ship. If this was shipped with these things in here, now everything would be destroyed, right? These panels would be all bent up because of the weight of this thing, right? Look at the size of the power transformer down here. It's absolutely monstrous. And that's pretty much it. The adjustments for this pre-driver chassis are right there. So when I put this thing together, I built it all so that I can just remove everything quickly if I need to fix this thing up, right? Because it's kind of hard to work on things in here unless, of course, you're changing a tube or something, right? If you're changing a tube, you just grab the tube and turn it and remove it and, service things, clean it up in here. But, to work on something like this in here, it's nicer to take it out and work with this on the bench. So just unplug this connector and unplug this here, and I can remove these little clamps here. The thing just comes off the wall and I can service it right on the bench. In fact, I have a test fixture that just plugs right into this that I built when I put this together, so I can mimic the VFO and everything, so I can work on this. All the drive levels and everything are all still the same. So that was a build from many years ago. Still works nice. More big resistors and transformers and stuff. Oh, these are the this is the neutralizing capacitor right here, and this is the shaft that would run out through the face. So this is just at a fixed amount right now. As you can see, it's just, there's nothing hooked up to the coupler right now. That VFO adjustment is hooked there. So it's set right at the right amount for the frequency that I'm normally on. Big E.F. Johnson potato slicer here. E.F. Johnson makes some really nice components and parts. They made these sockets as well. They were famous for making all of these old tube sockets and lots of ceramic stuff. So they did a really nice job. All the capacitors in here are all made by E.F. Johnson. And the backside of all the meters. And that's about it. Alright, this place is like 100 degrees and I'm out of here. The 810s say goodbye. And the 813 says goodbye as well. Thanks for stopping by the lab today. Hope you enjoyed this episode involving this big old AM broadcast transmitter. If you're interested in this kind of technology, high-powered RF stuff or vacuum tube electronics, right through to modern technology, surface mount stuff, this channel is the place for you to be. I feature all that kind of stuff here and repair all sorts of interesting things. If you're interested in having my understanding of electronics, you may want to head to my Patreon site and check out my ongoing electronics course there. Or if you just want to support the channel, that's great as well. So I hope you enjoyed this video. If you did, you can let me know by giving me a big thumbs up, then hang around. There'll be many more videos like this coming in the near future, touching on all sorts of different types and aspects of electronics. So until that time, see you later. Bye for now.